Yes,
Luis
Prof.
obtains his first degree in civil engineering at Universidad del Valle, Colombia. Then in 2009, he started his career at School of Civil and Environmental Engineering of Wits University in South Africa. He got his PhD from that university with the thesis title to assess the liquefaction potential of tailing dams using CPT, cone penetration test. So he is closely associated with the industry, as his philosophy is to take industry as the essential part of the research. He has already having the academic exchange at universities in Brazil, Canada, Saudi Arabia, and currently he is the senior lecturer on geotechnical engineering at Wits University. Actually, for our audience also, I can say he has he is one of the co-author of a classic page of paper. The title is Why Colas and Tailing Dam Disaster Occurs. That is in Science 2020 with Joel. So if you go to that, so you can get lots of about motivation about his work. So now I'll request Dr. Luis to start his presentation.
Professor Das, thank you very much for your kind introduction. Can you please confirm that you can see the first slide of my presentation on full screen?
Yeah, I'm able to see it, and it's very clear.
It's clear and
okay.
Perfect, but request you to please make your video on.
Is my video not on right now?
Yeah.
No.
Okay, let me see how I can sort that out. Let me start the video.
Yeah, perfect.
Yeah.
Okay, so now you can see my video and you can see my shared slide.
Yeah, perfect. Please proceed.
Thank you very much, colleagues. Thank you again, Professor Das, for that presentation, for that introduction, and thank you, Professor Reddy, for your presentation. The title of my presentation today is The Critical State Line of Non-Plastic Tailings. Allow me to begin the presentation by setting the context or the motivation for this research. Many, maybe all of you, might be aware that the safety record of tailings dams over the last decades has been not what we were expecting, has been unacceptable. And that tailings dam failures often result in large-scale liquefaction events, essentially large movements of the tailings that were meant to be stored in the tailings dams. So on the upper left part of the slide, I am showing you an image of the failure in Brumadinho, Brazil. I'm sure you've all seen the images. You've probably all seen the video of the moment of the failure. It was a catastrophic event. It killed over 250 people. Very recent, so very fresh in our memories. But of course, this type of event is nothing new. So I'm also showing you an image that is closer to my geographic location. This happened in Maritzburg, South Africa, back in 1994. In this case, it was a gold tailings dam that collapsed and killed 17 people, and the failure of the dam also resulted in liquefaction. So let's take a few minutes to address the question of why do soils, including tailings, why do they liquefy? So let's talk a bit about the mechanics, and to understand what is happening, we have to address the concept of the critical state line And two phrases are used to describe this concept, either the critical state line or steady state line. I tend to use both of them interchangeably, so please excuse me if in some slides you see CSL and in other slides you see SSL. They're both referring to the same thing. So this critical state line is defined in a three-dimensional space of void ratio, mean effective stress, and deviator stress. So in this case, I am showing a two-dimensional projection of that line that actually lives in a three-dimensional space. In this case, I am showing the void ratio versus mean effective stress projection. Now, the critical state line depends on the intrinsic properties of the soil. Meaning, by intrinsic properties, I mean mostly particle size distribution, particle shape, and mineralogy. If you change one of those, the critical state line of the soil will also change. And the idea behind the critical state line is that if you shear a soil specimen sufficiently, that specimen will arrive at a point of the critical state line and it will remain at that point. Once the specimen reaches its critical state, then the void ratio, the mean effective stress, and the deviator stress remain constant. You can see two lines on this slide, and there's the orange line, which represents what is a typical critical state line, the way it actually looks. And then there's the idealized line, which is straight. So the actual critical state line, the orange one, is not really straight, but as an engineering approximation, it's very common to work with a linearized critical state line in semi-logarithmic space. So why do I say semi-logarithmic? Because in this projection, the mean effective stress is on a logarithmic axis. And with any straight line, we need two parameters to define it. We need the slope and we need one point. The slope is typically represented with this Greek letter lambda, and the point is generally gamma 1, which is essentially the void ratio of the linearized critical state line at a mean effective stress of 1 kilopascal. So that is gamma 1. But of course, you could use any point. You could also use gamma 100, which would be the void ratio of the critical state line at a mean effective stress of 100 kilopascals. So you can think of this gamma 1 or gamma 100 as a y-intercept. So it's not really a y-intercept, right? Because it's a logarithmic scale, but we can think of it loosely as a y-intercept. And I'll mention just now why I'm bringing to your attention both gamma 1 and gamma 100. Something to know about the critical state line is that its definition is done by interpolating a series of points, such as shown for the two critical state lines in this picture. To get each one of those points, you need to run one triaxial test. It can be either drained or undrained, but each point of the critical state line represents one triaxial test. Then you perform a best fit through those points, and that is your critical state line. So it's quite a laboratory intensive product or parameter to come up with. So this line here, which is very nicely defined with about 15 points, well, it means that someone had to run 15 triaxial tests to arrive at that line. Now, notice something, that the critical state lines generally have data at around 100 kilopascals, but seldom do they have actual points at a mean effective stress of 1 kilopascals. So think about the upper line, for instance. If I were to ask you, what is the void ratio that corresponds to a mean effective stress of 100 kilopascals, well, you would come up here and you would probably need a bit of interpolation, and you can give me a reasonable estimate of what that void ratio is. As I have said, we would refer to that void ratio as gamma 100. Now, if I were to ask you what is the void ratio that corresponds to a mean effective stress of 1 kilopascal, well, you probably wouldn't be that sure anymore, because that would require a bit of an extrapolation. So you would probably tell me, look, it's looking like 0.78, but you wouldn't be as confident as your estimate of gamma 100. So your estimate of gamma 100 would be more confident than your estimate of gamma 1. And that intuition has a mathematical or statistical representation, and it is what we call the relative standard error. So this graph right here is summarizing an analysis based on 149 critical state lines in non-plastic soils that have been previously published in the literature. Now, I want you to notice two things. Actually, before I look at the green data points, let's first look at the red data points. The red data points are telling us the percentage of critical state lines whose domains include P prime. So you can see that very few critical state lines have data points at 1 kilopascals, but this is about 10%. But almost all of them, 90%, have data points at 100 kilopascals. This is what I was illustrating in the previous slide. Therefore, this has an effect on the relative standard error, which is nothing more than a statistical quantification of how certain we can be on the parameter. So we can see that we can be more certain because the standard error is smaller for gamma 100 than we can be for gamma 1. So although it is very common in the literature to find references to gamma 1, in this presentation, I will be referring mostly to gamma 100 going forward, okay? And this is my justification to why I depart from the convention of gamma 1 and adopt gamma 100 instead. Now, back to the critical state line and how it affects the mechanical behavior of soils, and in particular, how does it eventually help us determine whether a soil is susceptible to liquefaction or not. Now, here's again our critical state line in void ratio versus mean effective stress space. This critical state line essentially divides this space into two regions, a contractive region and a dilative region. Why do we call this region dilative? Well, consider a soil that is sitting at this point and has this steady or critical state line. When you shear that soil under drain conditions, remember, the premise is that that soil will move towards its critical state line. So because this soil is sitting below the steady state line, it will try to go up, not exactly vertically, right? But in general, it will try to go up towards its steady state line. In other words, its void ratio will increase, and therefore it is dilating. Conversely, for a soil that is initially sitting above the critical state line, well, it'll try to go down when you shear it to reach, this is shearing under drained conditions, of course. So it will go down to reach its critical state line. In other words, its void ratio is decreasing. It would be contracting. Now let's shift to undrained conditions. What would happen if I take a dilative specimen and I shear it under undrained conditions? Well, because the conditions are undrained, now no volume changes can occur. No volume changes can occur, and the void ratio must remain constant. The only way that this soil now has of approaching its critical state line is to move horizontally to the right. So what is happening? The mean effective stress is increasing, and because soils are frictional, the greater the contact stresses between those particles, then the greater the shear strength. So I am not including shear strength in this figure, but I hope you can appreciate that, well, if we have an increase in effective stress, the shear strength will necessarily go up. Conversely, for contractive soils, if we shear one of those under undrained conditions, then that soil, in order to reach its steady state line, it will have to move to the left because it cannot change its void ratio. And what is happening to the mean effective stress? It is dropping quite significantly. And if there is a drop in the mean effective stress, then there will also be a drop in shear strength. So I hope this illustrates that the relative position of the soil with respect to its critical state line will play an important role in defining the behavior of that soil under undrained conditions. To characterize that relative position of the soil, we use the state parameter psi, that state parameter which was introduced by a very widely cited paper from 1985 by Bean and Jeffries. This state parameter is essentially the vertical distance between the states of the soil and its critical state line. And it is defined in such a way that soils that plot above the critical state line, in other words, contractive soils, have a positive state parameter, and soils that plot below the critical state line have a negative state parameter, a negative psi. Right, so far I've been looking only at this projection of the critical state line, void ratio versus mean effective stress. But this is a two-dimensional projection, and I did tell you at the onset of the presentation that the critical state line lives in a three-dimensional space. So if we, for a complete representation of the critical state line, we're going to need a second two-dimensional projection. And that second projection is Q versus P prime. And in this projection, the critical state line always plots as a straight line that is going through the origin. Notice in this case, there is no semi-logarithmic space, right? Both the vertical and horizontal axes have natural scales. And because this straight line is going through the origin, there is no y-intercept. So all we need to define the critical state line in this space, Q versus P prime, is one slope. And that one slope is defined with that uppercase M, typically referred to as the critical state friction ratio. Right, so we have seen so far that the state parameter is useful to know to anticipate the mechanical behavior of the soil, and in particular, to determine or to assess its vulnerability to liquefaction. The challenge here becomes that we need the state parameter of the soil as it exists in situ. How do we determine the state parameter as it exists in situ? Now, you might be thinking, well, we can collect an undisturbed sample. But it turns out that that's not very practical with cohesionless soils. It becomes very difficult to collect undisturbed samples, and it can also be very, very expensive. So the approach to determine the state parameter in situ relies heavily on in situ testing. Now, what I'm going to describe here is the approach presented in this textbook, Soil Liquefaction, again by Jeffries and Bean. The approach says, look, to determine psi in situ, we're going to use CPT results, we're going to use the critical state line, and we're going to use other soil properties, and I'm not going into details here, but those other soil properties come from both additional in situ testing and additional laboratory testing. So in addition to the CPT and to the critical state line. So what's the idea? The main idea is you run a CPT and then you use the critical state line slopes, both lambda, the slope in the EP prime projection, and M, the slope in the QP prime projection, plus other soil properties to infer your state parameter from the CPT. Okay, what is the challenge? Well, the challenge is that as you are pushing that CPT into the ground, your probe, that cone penetration probe, is going through various soil types. And the gradation of the soils that that probe is encountering will vary from one depth to the next. And in the case of tailings, it can actually vary quite significantly, as we are about to see. And if the gradation that the probe is encountering is changing, then the critical state line is also changing, because remember, the critical state line depends on particle size distribution. So that leaves us with the question, well, then which of those critical state lines should we use to infer the state parameter from the cone penetration test results? So if you are implementing this approach, one of the first questions that you want to address is, how can we assess the range of critical state lines that exist in the tailings dam? Now, here is some data from a platinum tailings dam in South Africa. And this is just to illustrate this variation of particle size distributions that I was talking about. In this figure, we have the particle size distribution of 49 samples. And essentially, all 49 samples yielded a different particle size distribution. So considering that you have this range of distributions, your question is, well, for which of these particle size distributions do I determine the critical state line? And we must keep in mind that budgets will typically allow for 1, 2, or 3 critical state lines in my experience. So which of these materials should be tested? Let me start with some good news. The good news is that for the Q versus P prime projection, it doesn't make a difference. It doesn't matter. Regardless of the particle size distribution that you test, you are going to end up with pretty much the same Q versus P prime projection, and therefore the same value of M. Please remember that the slope of this line is uppercase M. And here I'm showing this example from Carrera et al. 2011, and their data applies to fluoride tailings, but you can see similar results for other types of tailings. So M is largely independent of particle size distribution. That's good for us. This does not mean that M is disconnected from the intrinsic properties of the soil. It is very much connected, but its greater dependence is on particle shape and mineralogy, which in many tailings dams remains pretty much uniform throughout the entire deposit. Now let's move on to the tricky part. And that is the EP prime projection. And that projection, void ratio versus mean effective stress, does depend on particle size distribution. So what can we do in that case? going back to the textbook by Jeffries and Bean, they suggest that we should examine the gradation envelope and pick a single representative gradation, assuming that one representative material exists. They also say that we can decide whether to test additional gradations, looking to both the coarser and finer sides of the in situ gradation envelope. So I want you to notice that the focus here is very much on the gradation. That's what the recommendation is telling us. Focus on the gradation. Let's have a look at an example of this approach. This image comes from the post-failure investigation report of the Brumadinho tailings dam. And here you can see that approach being put into action. So they have chosen a particle size distribution that is sort of like the average of all those gray lines that you see in the background. Those gray lines would represent all the in situ measurements from different samples. And then there is another, so they're going to determine the critical state line of this green particle size distribution curve, and then also going to the finer side and also to the coarser side. So they're sort of taking an average, fine, and coarse. And imagine if your budget only allowed for two, then we would probably have to focus on the fine one and on the coarse one. Now let's see some potential pitfalls of that approach. This data comes from a 2002 paper, and essentially they tested the critical state line of a silt, of a sand, that would be the green line, and of several sand silt mixtures. And here on this left-hand side, we have the critical state lines, again in void ratio versus mean effective stress space. Let's see what they find. When they determine the critical state line of the sand, they get this green line over here. Then when they start testing the mixtures, when they test the mixture with 7% fines, they get this. It moved down. 15% fines, down again. 25, 40, it keeps going down. Now 60% fines, if you thought it's going to go down again, well, not anymore. Now it goes up. And what about the silt? It goes up again. So much so that the CSL of the silt is very similar to the CSL of the sand. So consider this case. If you had tested only the silt and the sand, you would have concluded that the range of critical state lines is given by this, by the brown and the green line, and you would have missed out on the critical state lines that are defined by the mixtures of sand and silt. So testing only the extreme gradations can lead to an systematic underrepresentation of the range of critical state lines that actually exist in situ. Now, going forward, I am going to advance the argument that instead of focusing on gradations, we should be focusing on what the limit void ratios of the soil are doing. And by limit void ratios, I mean the minimum void ratio and the maximum void ratio, which are generally determined for soils by standardized tests in the laboratory. Now, why? To try and make my case, I present this graph, and I want you, there are three curves here, and I want you to focus for now only on the one in the middle, which would be representing a certain gamma. You can think of it as gamma 1 or gamma 100. I think it makes sense to think of it as gamma 100, since that's what I've been referring to. So this trend here shows us what we just saw in the previous slide. On the horizontal axis, we have fines content. So it is telling us that at 0% fines content, you have a certain gamma 100. And as you start increasing the fines content, the gamma 100 starts going down. In other words, the critical state line starts shifting down in void ratio versus P prime space. But after a certain fines content it starts going up again. Now, this is the argument often used to say that we have to pay attention to the fines content to understand what gamma n is doing. However, it so happens that the maximum void ratio and the minimum void ratio of a soil follow the exact same trend. As you start increasing the fines content, the limit void ratios initially go down, and after a certain fines content, which some of you might refer to as a transitional fines content, it starts going up again. So if gamma n is following the same patterns as E min and E max, then we have a rationale to try and explore correlations directly between gamma 100 and the limit void ratios. And by doing that, we are bypassing the fines content. So what is the advantage? Well, limit void ratios, first of all, capture changes in the entire particle size distribution, not only in fines content. And furthermore, limit void ratios are sensitive to changes in particle shape. And we know that those changes in particle shape also affect the critical state line. So it all sounds very nice, but of course the proof is in the pudding. Sorry, that's those are the dogs joining in on the presentation. So what happens when we look at the data? Do we actually find a correlation between limit void ratios and this gamma 100? Again, here we are looking at an analysis based on 149 non-plastic soils in general, both tailings and non-tailings. And we find that there is a well-defined correlation between gamma 100 and the minimum void ratio. By the way, there wasn't such a well-defined correlation with Emax. So I will focus mostly on E min going forward. The correlation is very well defined. However, there is scatter, right? And the scatter goes about plus minus 0.2 from the best fit line. So although I will be showing how this correlation is useful, I do want to make emphasis on the fact that this correlation is no substitute for triaxial testing. There is too much scatter in the underlying data. Now, in assessing the scatter of the data, we need to keep in mind that these data points are coming from critical state lines that had been previously published in the literature. So here I am pulling in data from different sources, from different laboratories, and that in itself is a source of scatter. And if you're interested in that, here I'm making a bit of a parenthesis, but I would recommend that you have a look at this paper. I have absolutely nothing to do with this work, but I just found it very, very interesting, in which the authors essentially take the same soil sample, they split it into something like 15 parts, and they sent it to 15 laboratories all over the world, and then they to determine the critical state line, and then they compare the different critical state lines that they obtained, and here you can see the scatter in their results. So this type of difficulties or challenges in the reproducibility of the critical state line will negatively affect correlations like the one that I was showing. Okay, I think I'm falling behind with time. I better hurry up. Right, so I am suggesting this gamma 100 versus E-min correlation. A natural question to ask is, well, does the finds content have an effect on the correlation? Here, I am dividing the data set into 4 groups of finds content, from clean sands, increasing the finds content, all the way to silts. The best fit line that I am showing on each graph is the same one. It is the best fit line of the entire database. And you can see that regardless of finds content, the data tends to plot around the same best fit line. There is a bit of a shift of the data for the silt, where one might argue that the silts are plotting mostly below the best fit line. However, this red outline here corresponds to this outline, which shows where the data points are plotting in this graph. So this is just to highlight that although there appears to be a shift, it is also true that there is a great deal of overlap between the position of these sands and these silts. So on that basis, my claim is that the correlation is largely independent of finds content, and that shouldn't surprise us because E-min can capture those changes in finds content. What about the effect of particle shape? So I am doing a similar analysis here, but now I am discriminating the data in terms of particle shape instead of finds content. So what we have on the left-hand side is mostly rounded particles, and on the right-hand side, mostly angular particles or mostly angular soils. And what you can see is that both soils with rounded particles and with angular particles plot around the same best fit line. So again, the gamma 100 E-min correlation is largely independent of particle shape. Now, I've spoken only about gamma 100. What about lambda, which is the slope of the critical state line in E versus log P prime? Well, when you plot the data, this is what you get, okay? And back in 2019, I said, look, this seems to be the best fit line for this data. Clearly, there is much more scatter, and the correlation is not as strong as the previous one that I was showing of gamma 100 versus E-min. But this best fit line, despite the scatter, is suggesting that there is an increase in E-min. Sorry, that when E-min increases, there is an increase in lambda. And here I've included that question mark because if you're thinking, no, come on, Luis, you're pushing our imagination too far now. There's really a lot of scatter here. Yeah, I don't blame you for thinking that. I do realize there is a lot of scatter, but we will be coming back to this data set. What I can say though is that yes, although the correlation is weak, at least there is some guidance. Okay, there is some guidance based on actual data that higher lambda seems to be possible only at higher E-min. On the other hand, consider what is often thought of as a guiding parameter for lambda. There seems to be this idea out there that soils with higher finds content will exhibit a higher lambda. However, when you look at the data for non-plastic soils, we see that the data does not support that correlation. At very high finds content, you may find low lambda, and at very low finds content, you may find very high lambda. So sure, this correlation is weak, but hey, but I prefer a weak correlation to no correlation. Right, so far I've been talking about non-plastic soils in general. Now let's see how that applies to non-plastic tailings in particular. And I'm going to illustrate that initially with an application of these concepts to a platinum tailings dam in South Africa, which you are seeing on the slide right now. Of course, there is a variety of particle size distributions at the dam, as one would expect. And you can take representative particle size distributions and determine their limit void ratios, both Emax and Emin. At some point, I used two methods to determine the Emin, but they're showing pretty much the same trend, so we don't have to worry too much about that. And then to try and determine the range of critical state lines in this deposit, our approach was choose this gradation with a 30% fines content because it has the lowest minimum void ratio, and choose this one with 10% fines content because it has highest minimum void ratio. And we also chose this one with 81% fines content because it has an intermediate void ratio. Okay, so I want you to notice, okay, first of all, it seems like we're back to the same thing, right? Low fines content, high fines content, and sort of like an intermediate fines content. Yes, but the guiding parameter is the minimum void ratio. The principle is different. Furthermore, in this case, choosing by Emin or choosing by fines content pretty much leads you to the same selection, but that may not always be the case. And furthermore, if I had to choose only two, then I would have chosen only 10% fines content and 30% fines content because those are giving me the highest and lowest Emin, and I would have left out this one with 81% fines content. So this is just a quick comment on critical state line testing and running the triaxial tests. Just keep in mind that those triaxial tests don't always reach critical states with steady readings at the end of shearing, and that for those cases, it may prove useful to implement extrapolation schemes to have a slightly refined assessment of the critical state line. So we describe those extrapolation schemes in the paper, and if you're interested, I would also recommend you have a look at Carrera et al. 2011, where those schemes are also described. Right, so here are the resulting critical state lines. Let's see if they fit the expected trend. So the gradation with the highest minimum void ratio plots on top, meaning it has the highest gamma 100. Intermediate minimum void ratio results in intermediate gamma 100, and the lowest minimum void ratio yields the lowest gamma 100, which is exactly what we would have expected from that gamma 100 versus Emin correlation. And going to the other projection of Q versus P prime, we see that the three gradations define essentially the same critical state line with a single value of M of 1.27, again, falling in line with our expectation. Now let's put the focus on tailings and not only on the tailings that we tested, but on tailings that had been previously reported in the literature. And to do these comparisons, we looked at something like, I forget the exact number right now, I think it was 25 tailings previously reported in the literature, including the 3 tailings gradations that we tested. And we also complemented our analysis with the database of other non-plastic soils. So we had like 132 non-plastic soils. The gray circular markers are the non-plastic soils, and everything else is tailings. Here is our gamma 100 versus Emin correlation. Notice that the tailings, the colored markers, are following pretty much the same trend as the other non-plastic soils. And I think this is a very important point to emphasize, because often we are told that, you know, tailings are like special and they're a bit mysterious because they're man-made and they don't have a geological origin. Rather, they were crushed in the mill. And yes, tailings are different in many ways, but also when you're looking at the fundamental properties, they will obey the same trends as other non-plastic soils. So this, and the same can be said of gamma 100 versus Emax space. Here we see a bit more of scatter. The data is a bit more spread out. But again, the tailings are following pretty much the same trends as other non-plastic soils. Now, coming back to the lambda versus E-min correlation, the scatter hasn't improved from that first figure that I showed you. But however, there has been a change in the interpretation that we make of this data. Previously, I had shown you like a best fit line, but for when putting together this presentation, my co-author, Professor Santamarina, actually suggested, well, what the data appears to suggest is an upper bound for lambda. So we have reviewed that interpretation and we are saying, look, the data supports that the upper bound for lambda is E-min divided by 3. So you can expect higher lambdas to be possible for high E-min, and they are less likely for low E-min. So it's a slightly revised interpretation of the data. And again, tailings following the same trend as other non-plastic soils.
Sorry to interrupt you. You have 10 more minutes, including Q&A.
10 more minutes.
Yeah, including Q&A, please.
Oh, thank you. Okay. And here some effect of mineralogy with quartz soils exhibiting generally lower lambda values. So, well, seeing that we have only 10 more minutes left for the Q&A, I'm going to skip the last 2 slides. I think I had already captured the essence of the work, and I'm going to go to the conclusions that the CSL parameters of non-plastic tailings follow the same trends as other non-plastic soils, that the variability based on extreme gradations can underestimate the in situ range of critical state lines, and that we can use the spatial variability of limit void ratios to assess the variability of critical state line parameters, both gamma 100 and lambda. The QP prime projection of the critical state line is largely independent of gradation. And these last 2 points I didn't get a chance to address, but essentially it means that we have more confidence on our estimates of gamma 100 than on lambda. Here are the references, and I finish by thanking the course organizers for the invitation, Wits University and King Abdullah University of Science and Technology, where I was hosted by my co-author, Professor Carlos Santamarina, and I thank the audience for your attention. Thank you very much.
Thank you, Dr. Luis. So now we'll go for this question answer session. Let me check. Now I request also all the participants to put their queries in the chat box. So there is a query from Bacchus. Thanks for the comments regarding the limiting strains in the track cell test. Outside of extrapolation and indirect measurement techniques, are there alternatives to find the CSL, critical state line? Do you think that this limiting strain explains the variability from the round robin testing, or is the calculation of the CSL subject to that much variability? Should I read it again, Dr. Luis?
Yes, a very pertinent question. I am not aware of other tests being used to determine the critical state line other than triaxial testing. So it seems like we have to live with the limits of straining that we can reach with the triaxial testing device. We can use enlarged end platings and lubricated plates to try and make the most out of those limits. As for whether that could be a cause for the differences observed in the round robin, I read that paper a few months ago already, so I don't remember that being a major cause of difference. I think most of the difference was coming from measurements in the void ratio of the specimens, which is a very tricky, I would say the most tricky component of running a successful triaxial test to determine the critical state line.
Okay. Any more query? I request the participants. Okay. So Dr. Luis, so I found lots of correlation you have developed. So just to find out those critical state parameters. So just can you tell me what are the abundant types of tailings you have considered for all these correlations? Like we understand also this bias as a tailing, so also this bauxite residue tailings, so also mine tailings. So that means it is something like if I want to go for the formation, like it was like a thermogravimetric type of formation, or it was something like from chemical type of formation, or it was mostly only the mechanical grinding and other types of tailings you are talking about.
Yeah. Thank you very much. It was non-plastic tailings. That's where our focus was.
Okay.
So I am going to take a guess here that most of these tailings would have come from hard rock mining, although there were also some oil sand tailings. So I think it was mostly those. I know that kimberlite tailings can be very, very plastic, and also some types of iron tailings can also be very plastic. So we would have presumably left those out and focused mostly on hard rock mining tailings and oil sand tailings.
Okay, then one more query has come in between. The ring shear test device is used to establish critical and residual strength of soils. Is particle orientation of non-plastic soil affect critical shear strength? Is particle orientation of non-plastic soil affect critical shear strength?
I know that there is a certain fabric that soils are expected to achieve at critical state. So you would imagine that particle orientation does play a role. Like, I define critical state line as living in a three-dimensional space. Some authors make the argument that we should think of it as living in a four-dimensional space where fabric represents that fourth dimension. So particle orientation might play a role there. That being said, for most non-plastic tailings, even the finer particles, they are rather bulky instead of platy. So I would imagine that it doesn't play a major role.
Okay. What is the sampling method used in this test with triaxial? Was there any effect on sampling method on CSL or SSL development?
The thing with critical state line testing is that you run the triaxials on reconstituted specimens. So sampling method plays absolutely no role here. You literally go to the site with a spade and a bucket and collect your tailings, because all of that, of course, it's a highly disturbed material, but all of that will end up being reconstituted in the laboratory.
Okay, so that means all they are disturbed sample. I mean,
they are disturbed samples, and what you have to make sure in the laboratory is that, you know, if you're going to define a critical state line using 8 triaxial tests, then that the 8 specimens used in those tests are as similar to each other as possible, same particle size distribution.
Okay. So, any more queries? Okay, so I didn't find any more queries. Thank you, Dr. Luis. It was a nice presentation on critical state soil mechanics. And yeah, so thank you very much. I didn't find any more queries, so thank you very much. And everybody appreciated some message only I found regarding appreciating your presentation. And it was nice to see lots of correlations to find out that particular critical state parameter. I remember in 2009 in ISSMG one presentation was there. So there they were saying whatever you do, finally, ultimately, you have to go to that critical state soil mechanics. Yesterday also, one of the speaker was talking about different failure of these tailing dams. Again, it was the critical state soil mechanics. So I'll tell all the participants to take home this critical state soil mechanics, even for this our tailings. Thank you, Dr. Luis. Now,
thank you.